All right, today we're turning a corner in our study of physics, how and why things move. Um, so we are looking at this chapter's work and energy. Okay, there are definitely some things that carry over, um, but there's definitely a difference. So by the end of this lesson, you'll be able to determine when work is done and when it is not, be able to calculate how much work is done by force, discern when work is positive and negative, and be able to describe and calculate power in terms of work. So no further ado. The variable for work is a capital W. The equation for work is force times distance, but so D is for distance. This is the component of force that is parallel to the direction of motion. Component of force that is parallel to the direction of motion. Okay. Component of force that is parallel to the direction of motion. The unit for work force is what? Newtons. The unit for distance is what? Meters. And Newton times a meter gives us a joule. The unit for work is joule. Okay. The guy's last name, capital J, is the abbreviation for joule. Okay. Newtons times a meter. Good with that? Okay. Oh. When is work done? And I had a lot of work to do this weekend. Sitting at my desk forever. Papers to grade. Homework to do. When a force acts on an object while it is moving. When a force acts on an object while it is moving, work is considered to be done. When a force acts on an object while it is moving. So I want you to consider, when would work be equal to 0? what scenario or scenarios can you come up with where work would be equal to 0? Go ahead and tell your neighbor. You guys are really far apart.
She's going to, she said like later in the
Okay. All right. My guess is you came up with if it is not moving, so distance is 0. If there are no forces acting on it, like when force is equal to 0, so like threw a baseball in outer space and it's just like no forces, no work. Correct. Both of those are correct. It's not moving if there's no forces acting on it. Now, but here's a question. Is it possible for a force to be acting on an object and the object is moving, but no work is done? Is it possible for an object to be moving and a force to be acting on it, but still no work is done? Talk to your neighbor. What do you say? Is it possible? Is it possible for a force to always be acting perpendicular to the way it's moving? So would there be any component of that force that is acting parallel to the direction of motion? Nope. Okay. So that's our third scenario. So if force is acting perpendicular to the motion, then no work is done. Good with that? All right, give this one a shot. Tell your neighbor. Correct answer is D. Okay, so even if I'm struggling to support something, it's like if I'm not moving it, no work is done. Good. Next question. Guess what my suggestion is going to be? Draw a free body diagram. Thumbs up when you have a guess. Just make sure we're all like tracking here. All right. So for this, I'm just looking at tension. Which component of tension is acting parallel to the direction of motion? The whole thing, FTX or FTY? FTX. So this is FTX times distance. That is equal to the work done. Okay. Notice I'm asking for the work done by tension only. I don't care what friction is doing or gravity or anything else. I just care about the work done by tension. That's what I'm asking for. Go ahead and tell your neighbor. Tell them how you got there. Correct answer is C. Use sine, cosine, or tangent. Cosine. Here we go with that. Cosine of 60 gives you 0.5 times 600 gives you 300 times 20 meters, 6,000. And just super fast. So I have cosine of 60 is equal to ftx over 600. ftx is equal to 300. So I have 300 newtons times 20 meters gives me 6,000 joules. Good. We'll come back to this scenario in about 10 minutes or so. All right. When is work positive? When the force is acting in the same direction as the motion. And work is negative when force is acting in the opposite direction as motion. Okay. So, work, however, is a scalar, and there is no direction. Work is a scalar measurement which does not have direction. But I thought you just said the work can be positive or negative. Yes, that is true. For the first time in this class, positive and negative do not communicate direction. Okay? Because work is a scalar. That does not make sense at all to me. Well, here's the idea. So, energy has been a really big topic throughout your science education. Like you learned in elementary school about energy. Energy cannot be created or destroyed. Very good, class. Okay? You've been like, that's been hammered into your brain since elementary school. Okay? But we haven't talked about energy at all so far. Okay? we've come up with work, this idea of work, this measurement of work, to help us understand how force affects energy. Okay? So when we say a force does positive work, that means the force is giving energy to the object. Okay? When work is positive, that means it's giving energy to the object. And force is negative. Sorry, when work is negative, this means the force is taking energy away. Okay? So this is looking at, you look at direction of force to determine the sign of work, but the interpretation of what that positive and negative work is looking at how that force, is the force a taker or a giver of energy. That's what this is at. That's what that is capturing. Okay? Good with that? All right. Give this one a shot. What should you do first? Free body diagram. Okay, you don't have to just set up. I just want you to do the free body diagram. The setup, you don't have to do that for this chapter. But the free body diagram, definitely. Thumbs up when you have a question. Sorry, when you have an answer. Have a conversation. All right. There we go with the free body diagram. Okay, it's sliding down the ramp, and you're trying to prevent it from crashing to the ground. Okay. All right. So I'm going to move on from this question. How many forces are doing negative work? Same scenario. Talk to your neighbor. How many forces are doing negative work?
Wait, what? Then that's just like I know, but it's not like thing.
Okay, correct answer is 2 forces. Okay. Applied force and friction are acting in the opposite direction of motion. Negative work being done. What about positive? How many forces are doing positive work? Talk to your neighbor.
Nerd's not this.
Correct answer is 1. Okay, is any force acting purely parallel to the direction of motion? In the same direction as motion? No, but is there a part of gravity that's acting parallel to the direction of motion, like in the same direction of motion? Yes. We tilt their axis, FGX is in the same direction as motion. It's doing positive work. So force of gravity is doing positive work. How much work is normal force doing? Why is it doing none? It is not parallel to the direction of motion. It is acting perpendicular to the direction of motion. No work is done. So our original question is how many forces are doing work? D, 3 of them. Applied force, friction, and force of gravity. Good with that? Okay. Going back to our drag in the box. Talk to your neighbor.
Look at this. This tire. That's not that's the jacket.
Okay, correct answer is negative 4,000. Is everybody good with that? Acting in the opposite direction of motion. There is acting parallel to the direction of motion, so you don't have to take any components. Good with that? Okay. Next question. Bless you. Bless you. Bless you. Tell your neighbor.
Oh shoot, yeah. That's true.
Correct answer is D, 0. What about normal force? Also perpendicular to the direction of motion. So quick recap. Originally we said the force of tension is doing 6,000 joules of work. And then we came up to the conclusion that friction is doing negative 4,000 joules of work. Gravity is doing none. So now, what is the net work or the total work done on the box? Figure it out. Okay. Correct answer is? Correct answer is? Got a vote, 2 votes for A. Okay. So, to find the net work, the way I kind of coached you how to do it on this one was adding up all the works done by each individual force. Okay. You could also find it by finding the total force that's acting parallel to the direction of motion multiplied by the distance. Also, we'll find the net work. Okay. So in this case, that would be force of tension in the x direction minus friction times distance. Force of tension in the x direction, we concluded, was cosine of 60, 1/2 times 600 is 300 minus friction, 200 newtons times a distance of 20 meters. So this is 100 newtons times 20 gives us, wait a minute. That's what, whoa. That's what we got for the other one. Okay, so either way you do it. The way I coached you, we had already figured out the individual work done by all the forces, so adding them up would be the easiest way to do it. But if you just like come into a problem, like here, find the net work, that might be easy. Okay, good there. All right, we talked about that. All righty, next type of measurement is power. Okay, power is the rate at which work is done. Power, the rate at which work is done. Or how quickly work is done. How quickly work is done. Power. Power, power, power. Okay. So the variable for power is a capital P. The equation is work over time. Okay. That makes sense from the description. The rate at which work is done. Okay. The unit for power what's the unit for work? Joules. Unit for time? Seconds. A joule per second is equal to a watt. A what? A watt. Wait a minute. I've heard of those things. Aren't those the things on light bulbs? Yes, they are. And we will continue that conversation next semester when we start studying electricity. Okay? But for right now, we're going to put a pin in that, and we're just going to say that watts is the unit of power. It looks at how many joules per second, how quickly work is done. Okay? Now, just like for distance in science, we're going to use meters, but in America, we like to use miles, okay, or feet. In science, we like to use watts, but in America, we use horsepower. Is a different unit for power. Okay, and this came from James Joule, the guy where Joules. He did an experiment. He's like, how much power does an average horse produce? Like, and so he like averaged 1,000 horses and came up with this horsepower. Okay, so 1 horsepower is equal to 746 watts. Okay, 746 watts. Okay, so you're like, truck has 200 horsepower. I'm like, that's how quickly it can do a job. Like that's pretty fast. Okay. So quick example problem. I'm gonna turn you loose on. Bubba.